How are you today? Assalamualaikum warahmatullahi wabarakatuh. Hello, everybody. How are you today? I hope you are in the good condition. Today, our class is about we will learn on the chapter number 2. That is the properties of pure substances. So first of all, I would to thanks to my fellows, my colleagues from Shahlam, Dr. Idris Saad, and also Dr. Al Hassan Salami, and also Dr. Noor Afifah, because of their efforts to write down or to produce this slide of thermodynamics books. So as you see, this is, as I said last week, this is MEC 451, but it's also same as MEN 462. Okay, so before I start to introduce the lecture notes based on chapter number 2, the properties of pure substances. So let me give some information or some statement for you all to know or also should be able to obtain within this chapter. Okay, actually, it have three parts of this lecture. The objective of this chapter number 2, part number 1, is students should be able to know the introductions of the concept of pure substances, and also you should be able to know the when we discuss the physics of the phase change processes. Um, that is part number 1. The second part of this chapter is uh, you all should be able to illustrate the PV, PV, PT properties diagram. That means P stands for pressure, small v stands for specific volume properties diagrams. Also, you should know the temperature versus specific volume, like properties diagram. And also, you should able to know the pressure versus a specific volume versus temperature surfaces of pure substances. The next objective is you should also able to demonstrate the procedures for determining the thermodynamics properties of pure substances from tables of properties data. Okay, that is for part number 2. Part 3 of this chapter, uh, students were able to describe, okay, describe the hypothetical substance, that's mean ideal gas, and the ideal gas equations of state. Then you should able to apply these ideal gas equations of state in the solutions of typical problems. Okay, these all three parts you have to uh, able to know and also can apply in the situations of cases in thermodynamics. Okay, let's go on to the properties chapter number 2. Okay, the properties of pure substances The sub-contents on this chapter. Number one, uh, and number two is part one. Okay, where we will discuss on the pure substances, that is on gases and phase change processes of pure substances. Also the properties diagram for phase change process. Also we will look on the compressed liquid, saturated liquid, saturated vapor, superheated vapor, the quality of the vapor, the temperature versus specific volume diagram, and the pressure versus specific volume diagram. So that is part 1. Okay. After that, in part 2, I will discuss with you about the properties tables, focus on the water and also refrigerants 134A. And the next one is the part 3, the ideal gas equation of states, and also the ideal gas law. So we go for the part number 1, pure substance. As usually, the first thing before we go further on this chapter, we will have to know about the definitions of the term that will be used in this chapter. Okay, first is pure substances. What is that? A pure substances or a pure substance. Actually, this substance that have a thick chemical composite throughout. That is the definitions of pure substance. Okay, but if you look on the statement number 2, actually the pure substances does not have to be a single chemical element or component. However, if a mixture of various chemical elements and components also qualified as a pure substances, as long as the mixture is homogeneous. Okay, example as the air. Air is a mixture of several gases. Okay, but it is considered to be a pure substance. Okay, because air have several gases, gases that this mixture is homogeneous. So the mixture of liquid and water vapor is a pure substance. But a mixture of liquid and gases air is not. Okay? Okay, so this is the examples of pictures, figures, also pictures, what I am explaining. This is my program and this is air. And vapor and liquid for water. Okay, this is you can consider as a pure substance, but if a liquid uh, and the gases of air is not. Okay, because these two phases are not homogeneous. So another example we can put here is water, solid as a liquid and also vapor gases, and also a mixture of liquid water and water vapor, carbon dioxide, that is one an element of chemicals, nitrogen is a thick chemical composition throughout, and also as I said, as the air, as long as there is no change of phase. Okay, the mixture of gases such as air, as long as there is no change of phase. Okay, that is we can classify as a pure substance. So for this scope in Thermodynamics 1 and the end for 462, we are only concentrate on the water, refrigerant 134A, and also ideal gas. So let's look on the phases of the pure substances. So actually, the substances exist in different phases. Okay, either as mentioned here, three physical phases, that means solid, liquid, and also gas. So the definitions for solid is the molecule are arranged in three-dimension pattern. So in theoretical, the high force of the attraction between each molecule keep them in the split solution. That is this substance become as a solid. If it's in the liquid phase, what happens? The molecules are not longer at fixed position relative to each other, and they can rotate and translate freely. And that is if the phase are in the liquid. And if the phase of the substance is in the gas, the molecules are far apart from each other and the molecule order is not existent. So it moves above the random, okay, the molecule moves randomly, continually colliding with each other and the wall of the container they are in. Okay, that is when the phase of substance is in the gas phase. Okay, so as you see in figure 3.4, A is a molecule attractions for solid. B, okay, B is for liquid, and C is for gas. Okay, this is the kinetic diagrams or also the picture how the molecule in the solid are kept at their positions by large spring-like intermolecular forces. Okay, this is the examples. Okay, so there are many practical situations where two phases of pure particles coexist in equilibrium. Okay, so example of water exit as a mixture of liquid and vapor in the boiler and the condenser of a steam power plant. Okay, another example is the refrigerant. Okay, change phase where the refrigerant is the substance in the refrigerant can change the phase from the liquid to vapor in the freezer of the refrigerator. So in this section, it's focused on the liquid and vapor phase and the mixture of these two. So all pure substances exhibit in the same general behavior. So I will show the two experiments of boiler water that it will show the behavior of the pure substances. Okay, number one, I will show on the temperature versus specific volume diagram, where it increase temperature at the constant pressure. And number two, decrease pressure at constant temperature, where I will show on the pressure versus specific volume of diagram. So this experiment number one, where we increase the temperature at constant pressure. Uh, if you look when the experiment has been done and the result we plot in the temperature versus specific volume, the graph obtained is like plotted. Okay, so uh, state number one, state number two, state number three, state number four, and state number five represents the situations how this experiment occur. Okay, first when we heat the water at the temperature 180 m, sorry, the pressure 180 m, the temperature 20 Celsius. What happened? We heated the water as in the phase, in the liquid phase. That is, in these conditions, the liquid is at the compressed liquid. At step number two, the heat is continued given to the liquid, compressed liquid, And what happened at this time, the temperature of water will become 100 Celsius. Okay, at we look on the TV diagram at 100 Celsius, but the pressure is still 9 pm. Water exists as a liquid that is ready to vaporize. Okay, and when it's ready to vaporize, the liquid uh, to vaporize at 100 Celsius, we call it as a saturated liquid. So this is the line of the saturated liquid. Okay, so at these situations, at state number 3, the temperature is constant. Okay, 100 Celsius. But at these conditions, there are two phases. Number one is saturated liquid, and another one is saturated vapor. Okay, so as more heat is transferred, part of the saturated liquid vaporize. So these conditions, we call it as a saturated liquid vapor mixture. You see, this is the situation graph that reflects or mention this term of saturated liquid vapor mixture. So more heat, okay, more heat is transferred to the phase. So what happened here? The temperature also remains constant at 100 until the last drop of liquid is vaporized. So at this end of the liquid has been vaporized 100%. So we call it as a saturated vapor. Okay, saturated vapor. So this saturated vapor is at the state of number 4. Okay, this is the situation. Ini keadaan dia. Okay, at that position. So at state number 5, as more heat is transferred, the temperature of the vapor state start to rise. Okay, that means the heat transfer masuk dalam that liquid ataupun uap tadi tu. So the temperature has increased to 300 Celsius, and this situation we call as a superheated vapor, and this is the line of superheated vapor. Okay, okay. So now I will try to give you the knowledge of the TV diagram of constant pressure change processes of pure substances at various pressure, numerical various for water. So as this diagram, if the pressure is increased, we will find that, okay, so temperature versus specific volume. So the line in the graph of TV diagram here is a pressure. So when the pressure increase, we found that water will start boiling at higher temperature. Okay, so this is critical point. So it will boil. This is a saturated liquid. So as you see here, the temperature is different. Okay, different. Specific volume of the separated liquid increase. So specific volume will be increased. Okay, as you see here, will be increased. And specific volume of the separated vapor also decrease. So here, what happened? Uh, small v is decreased. Okay, from low pressure to high pressure. That is the significance of the uh, founding of the result that we found from this experiment. Okay, so as the pressure is increased further, the saturation line will continue to get shorter, and it will become a point when the pressure reaches 22.06 megapascal. Okay, 22.06 megapascal. So this point is also we call as a critical point. Okay, this point. But di mana yang saya tunjuk ni, I show this point. This critical point where it is a point with the saturated liquid and saturated water state are identical. Okay? they are sama. So the temperature, pressure, physiology of the substance at critical point are called respectively the critical temperature, critical pressure, and also critical specific volume. So at pressure above the critical pressure, okay, when the pressure is in this line above from the critical pressure, there will be no distinct phase changes in the air outside. Dia tidak ada perubahan dah bila lebih daripada critical point. So it is customary to refer to the substance as superheated vapor at temperature above the critical temperature and as compressed liquid at temperature below the critical temperature. Okay, that is one important thing that you have to know. When what happens when critical point, what happens to the pressure, and also what happens to the phase of liquid, mixture, and also vapor. Okay, this will show to you the term that important students to know, because based on this TV diagram, you have to know all these 1, 2, 3, 4, 5, 6, 7 terms uh, of the statement. Okay, okay, for the definition of compressed liquid. Okay, so when we see this is a compressed liquid region, okay, this at the left side, this one is the compressed liquid region. So below this line, curved line, this is a saturated liquid vapor region. Okay, and of course at the right side is superheated vapor region. So the boundary that uh, the boundary in between liquid and saturated liquid vapor is called saturated liquid line. Okay, saturated liquid line. So what is saturated liquid? Saturated liquid actually a liquid that is about to vaporize. Okay, this is saturated liquid line, and saturated liquid is liquid that about to vaporize. That means if the liquid is come near to this green point, so it will vaporize to vapor. Okay, it will vaporize. That is means saturated liquid. Saturated vapor, the vapor that is about to condense. Okay, so when it's called as saturated vapor, this line is saturated vapor. The vapor and liquid will become condensations. Okay, will be about to condense. So, saturated liquid vapor mixture is the state at which the liquid and vapor phases coexist together. So, at this area or at this region, these two phases, that's mean liquid and vapor, are mixed together. So, at superheated vapor is a vapor that is not about to condense. Okay, not saturated vapor. So superheated vapor. At this saturation, superheated vapor, so is 100% vapor. So the saturation, the vertical line at PV diagram, this is a condition in which a mixture of the vapor and liquid can exist together at a given temperature and pressure. At saturated temperature, that may be put as a T saturated, T set. Okay, as mentioned here, as shown here, T set. It is the temperature at which a pure substance changes phase at given pressure. So if we look at point here and also at point at the right side, this is where the phase in the changing phases. Okay, from liquid to mixture, also from mixture to vapor. Okay, I continue the slide. Okay, still in experiment number 1. So the temperature at which the water start boiling depends on the pressure. Therefore, if the pressure is heat, so the boiling temperature, water boil at 100 Celsius at 1 atm. Okay, so for the pure substance, it is the fine, the sorry, it is the finite relationship between saturated pressure and saturated temperature. The higher the pressure, the higher and saturated temperature. Okay, so you can look at this graph, pressure versus temperature. So the higher temperature, so the higher of the pressure. Okay, definitions of state of the substance, also PV diagram. So here what it show, I only want to show you uh, this kind of the graph of T versus small v. So based on the state postulate specified by two independent and intensive properties. So intersection between two intensive properties is the state. So as we look compressed liquid, as I mentioned, the right side region is compressed liquid. So if the temperature of the liquid is lower than the saturated temperature as for the existing pressure, so example we put pressure number 1, P1 here, okay, pressure number 1 at that line here. So the temperature is less than T saturated. Okay, so the temperature here is less than T saturated, that means below than T saturated. Okay, ataupun P1. So saturated liquid. Saturated liquids also, if a substance exists at a liquid at the saturation temperature and pressure, that means V is equals to Vf or V saturated. V, this is the scale of V. So if the point or the state at the saturated vapor line here, if the dot point is at this line, we put it ataupun we categorize it as VF. Okay, VF is specific volume for fluid. Okay, this fluid. Kalau kita tu ada pada garisan kiri sebut. If this state point is in this saturated vapor line daripada critical point until below here, we categorize this state as VG. Okay, G is for gas. If we plot TV, but if we plot TH, dia akan jadi HG. Kalau TS, it will become SG, and TU, it will become UG. Okay, the subscript for the subscript for this F is saturated liquid, F is fluid for saturated liquid, G is gas for saturated vapor, and if F G, it is the difference between G and F. Okay, Fg is G minus F. So the saturated liquid vapor mixture is the region between this curved line. Okay, the state at which the liquid and vapor phase coexist in the equilibrium. So V ni lebih besar daripada VF. So VF here, example. So V is bigger than VF and smaller than VG because VG is here. So V is smaller than VG. So if saturated vapor, what its name, it is a substance that exists entirely at vapor of saturated temperature. So if it happens, V is equal to Vg. Okay, if in this case called saturated vapor. Superheated vapor, it means that when the vapor is at the temperature greater greater than the saturated temperature. Example, if the temperature is less than T saturated, so T saturated is in the vertical line. If the temperature is bigger or we take T, if temperature is less than T saturated, that means below of T saturated, so it will be called as a superheated vapor. So T is okay. I think this is a wrong statement. Actually, T is greater than T saturated. That means T saturated is greater than T is greater than T saturated. So the situation is in the saturated vapor. Okay, yeah. This one is terbalik terbalik. Okay, we move for the experiment number 2. Okay, for the experiment number 2, this is for the discrete pressure with constant temperature. That means P versus specific volume diagram. So we consider in this experiment, we put the piston cylinder device. This is cylinder. So this is a piston. And then in that cylinder, it have a liquid water at 1 megapascal and also 150 Celsius. Okay, and this water we heat up with the burner. Okay, so what happened here? The water is allowed to exchange heat with the surrounding, so the temperature constant. So as the pressure decrease, okay, as the pressure decrease, the value of the water increase slightly. Okay, so let's look on the PV diagram. When the pressure reaches the saturated pressure volume at the specific temperature, example 0.4762, the water starts to boil. Okay, so during this vaporization process, both temperature and pressure remain constant, but the specific volume increase. So look, once the last drop of liquid is vaporized, so further reduction in pressure will result in the further increase in specific volume. So this is the result after experiment. So as you see here, the pressure is at the vertical, okay, vertical. On the horizontal is a specific volume, and the line inside this PV diagram, this is the temperature. So at the top, at the top is higher temperature, below is lower temperature. So it is different from PV diagram. So if you look back on PV diagram, inside the diagram is pressure. Okay, pressure below is low and then increase upwards. Okay, and the increase ni macam as a bentuk tangga lah. Okay, ada tangga sini, naik kat sini satu, dia naik kat sini tangga. Tetapi ini for PV diagram, but for PV diagram, dia adalah daripada atas turun ke bawah. Okay, bentuk tangga juga tapi bukan bentuk naik daripada kosong ni, sebab dia turun ke bawah. Okay, tapi ia adalah temperature, not pressure. Okay, PV diagram. So for saturated pressure, P separated yang ni, okay, at this side of picture, the pressure at this substance changes place at the given temperature. So at the temperature berubah, so the pressure changes. Substance tu akan berubah. Masa ada. Okay, this one, as I mentioned, sama macam tadi, as a PV diagram. So, every point state that have in the separated liquid line here, we call that as subscript F. Okay, whether we use V, H, S, or U. Also, if the states have at this saturated vapor line, uh, we call as a G, okay, saturated vapor, VG, HG, SG, and UG. Okay, so this is all the things that you can read for compressed liquid. If the pressure of the liquid is higher than the saturated for the saturated, so P is greater than P saturated. Okay, it is same as the temperature. Okay, the earlier slide. Okay, for PV. Okay, but the difference is only we change the temperature here, vertical, still here as pressure. Okay, so look at here. Here is pressure versus specific volume. Okay, now we look on the extending the diagrams to include the solid phase. Okay. So at this slide, it shows that triple point pressure and temperature. A substance exists in three phases, namely equilibrium. So this is how it shows if we use in the one system. It has solid, liquid, and vapor, and then we want to plot it to PV diagram. So the diagram, it will show like this. It has a critical point, and the solid is at here. Solid plus liquid is at this position, and this is liquid position. Okay, liquid region. So this is a mixture of liquid and vapor, and this is also pressure. Okay, then we quite demotivate, or we like, it is quite difficult. As you know, we are learned about thermodynamics, thermofluids. So we are only focused on the liquid vapor and vapor. We not focus on the solid and solid liquid. Okay, this is for this is solid is not interesting in thermodynamics. We only interested to solid vapor and also vapor. Okay, this is only the knowledge how it shows the PT diagram. Okay, for PT diagram, that means extending for the diagram to include the solid phase. So for the sublimation, passing from the solid phase directly into the vapor phase, that means the lompat daripada solid terus kepada vapor, not kepada solid, liquid and vapor, tapi the jump, okay, one step of the phase. So it has a sublimation. So it is solid region. So when it happen, dia tak pergi dah kepada liquid kat sini, dia tak jump ke sini, dia terus jump ke sini fasa tersebut. So dia akan cross barisan yang dinamakan sublimation. Okay, sublimation. So melting line, okay, like melting line, this line is the substances that contract on freezing. Okay, liquid, this is liquid. So when it crosses this line, liquid cross this line, it will become melting. Okay, as low pressure below the 3.5 solid vaporize without melting first sublimation. So solid will go to the liquid. Okay, solid will reach to the liquid when it crosses the melting point. But if the substance expand on freezing, so this that point, okay, sometimes the solid also still in the phase of solid in the melting, and this is expand of freezing. Okay, expand of freezing. So for liquid to change to the vapor, it will cross the line of vaporizations. Okay, where the vaporizations will end up with a critical point. Okay, critical point. So this is just a knowledge to for you to know the PVT surfaces. present a great deal of information. That's one. So this is a 3D diagram for freezing, or concept of freezing, and also expand on freezing. Okay, this is 3D diagram, pressure, volume, and temperature. So the diagram is show like this for these three phases of substance. So as you see, this is a solid, liquid, liquid. But in thermodynamics, in your level of first degree, you will be only consider on the 2D diagram. That means temperature versus specific value, or pressure versus specific value, or that kind of cases. Okay, just only on PV or PV diagram. Okay, can I continue? Okay. We look more, okay, on the definitions of latent heat. Okay, latent heat. What is that? Okay, actually, latent heat is the amount of energy that means absorbed or released during the phase change process. That means when the solid will change to the liquid, okay, at these situations in between line or in between changes, the energy that absorbed or also release at these situations, we call it as latent heat. Okay, so the latent heat of fusions is the amount of energy absorbed during melting. So it is equivalent to the amount of energy released during freezing. Okay, for latent heat of vaporizations, the amount of energy absorbed during vaporizations, and it is equivalent to the energy released during condensation. So the magnitude of the latent heat actually depends on the temperature and pressure at which the phase change occurs. Okay, that you have to remember. Okay, this is an example. At 180 atm pressure, the latent heat of fusions of water is 333.7 kilojoule per kilogram. That's 1 kilogram. The latent heat is 33.7 kilojoule, and the latent heat of the vaporization is 226.5 kilojoule per kilogram. It is a lot of energy that we need to make it vaporize. Okay, and also a lot of energy that we need to fuse with the water. Okay, that is called latent heat. Enthalpy. Okay, capital H, and the unit for enthalpy is kilojoule. If small h, we call it as a specific enthalpy. Where when it called as a small h or specific enthalpy, we divide this enthalpy with 1 kilogram of mass. Okay, that is for small h. So enthalpy actually, this enthalpy is a properties. Okay, enthalpy is the properties. That means properties like uh, you know the properties of temperature, you know the properties of pressure, you also know the properties of volume, but enthalpy also be one of the properties, one of the characteristic of uh, substance. Okay, we call it as enthalpy. So for example, for an open system such as figure aside here, okay, internal energy, pressure, specific volume can flow in and out the system because it can flow inside and then go outside. Okay, control volume. So entropy is a thermodynamic quantity, okay, equivalent to the total heat content of the system. That is the definitions of enthalpy. Okay, it is a thermodynamic quantity equivalent to the total heat content of the system. So when we want to express this entropy in terms of formula, so it will become the H is equals to internal energy plus with work or PV. So when you have energy work combined or plus the internal energy, so these two properties combined together, it will become enthalpy. So the small h, as I said, U plus PV, and the unit is kilojoule per kg. So the enthalpy of vaporization that's referred to HFG, latent heat of the vaporization, is the amount of energy needed to vaporize a unit mass of saturated liquid at a given temperature or pressure. Okay, so if we look on the T or P diagram versus specific volume or versus entropy, so the amount of energy that absorbed or that needed is from state number one. If we put here number one, here number two, so at minimum number one to number two, this is the energy needed, okay, to vaporize the substance from uh, from liquid to vapor, 100% vapor. Okay. Um, Now we come to the properties table. So for the properties table, this is part number 2. Okay, so that's all for part number 1 in chapter number 2, properties of pure substances. Okay, we will continue on chapter on part 2. Okay, thank you very much.